Every year in the United States, about 27 billion square feet of drywall are produced. That's enough to lay a continuous path from the Earth to the Moon, and still have enough left for the way back. Imagine millions of tons of stone torn from the depths of the Earth, passing through giant crushers, furnaces, and conveyors to become the smooth walls of our homes. But the real magic of this process begins where ordinary gray stone becomes a thirsty powder and gains the ability to become stone again. Watch until the end, and you'll learn the secret that makes this possible. The numbers behind drywall production in the United States are not just big, they're astronomical, and they tell a story of how the country builds, renovates, and breathes. In a recent year, factories in the United States produced approximately 27 billion square feet of drywall panels. This number is so colossal that it's hard to comprehend. Try to imagine, if you laid out all this drywall, you could create a continuous 3-foot wide path that would stretch from the Earth to the Moon and almost halfway back. Or you could completely cover the entire territory of the state of Delaware twice with this amount of sheets, and still have some left over. This endless stream of building material is not just a physical product, but a powerful economic indicator. The market for these panels in the United States is valued in the tens of billions of dollars, reflecting not just the cost of the material itself, but also thousands of jobs in mines and factories, in logistics and construction. It all begins not in the workshop, but much earlier, in the quarry where gypsum is mined. This is a natural mineral, a stone that formed millions of years ago from ancient seas. It can be white, grayish, sometimes with pink veins. Huge excavators dig into the gypsum deposits and load dump trucks with boulders of this stone. These trucks bring tons of gypsum to the factory and dump it onto the raw material yard, creating entire mountains waiting for their transformation. The first stage inside the factory is coarse crushing. The gypsum boulders fall into the giant steel jaws of the primary crusher. With a deafening roar and grinding, the machine breaks the large stones into smaller pieces, about the size of a fist. This is just the beginning. Then, this crushed gypsum is fed by a conveyor belt to secondary mills. Here, dozens of steel hammers, spinning at insane speeds, break these pieces into even smaller fractions, turning them into something like coarse gravel. But even this is not enough. The final stage of grinding turns the gypsum into a fine powder, like talcum. It becomes so fine that it resembles flour or dust. This powder is the main raw material, but it still hides a secret that needs to be unlocked. The next step is one of the most important and interesting. This is a process called calcination, and in essence, it's the controlled drying of gypsum. The thing is, molecules of water are locked within the crystal structure of natural gypsum. To allow the drywall to harden, this water must be temporarily driven out. For this, the white powder is fed into a huge, slowly rotating furnace. It looks like a giant drum, tilted at a slight angle. Inside this furnace, a very precise temperature of about 300 degrees Fahrenheit is maintained. The gypsum powder, slowly tumbling inside the drum, heats up, and the water bound to it turns into steam and evaporates. Chemically speaking, gypsum turns into calcium sulfate hemihydrate, but in simpler terms, it becomes thirsty. Now this powder, which is already called building gypsum or stucco, has a unique property. If you add water to it again, it will greedily absorb it and turn back into a solid gypsum stone. It is this property that is the basis of the entire production. The resulting hot powder is cooled and stored in giant silos, resembling towers, from where it will be fed to the main production line. And now the most spectacular part begins, the creation of the sheet itself. In the workshop is a huge, hundreds of meters long conveyor. At its beginning stand 2 giant rolls of special dense paper, cardboard. One roll for the face side, it's perfectly smooth, white. The other for the back side, it can be a bit darker, grayish. The tape from the bottom roll, the face side, unwinds and lies on the conveyor, forming an endless track. Simultaneously, in a giant mixer, similar to an industrial food processor, the core is prepared. Our thirsty gypsum powder, water, and a whole cocktail of various additives are continuously fed into it. Each additive plays its role. Foaming agents make the gypsum mass lighter and more porous, like whipped cream, to reduce the weight of the sheet. Plasticizers make the mixture more fluid so that it spreads evenly. Accelerators or retarders allow engineers to perfectly control the time it takes for the gypsum to set. Starch helps the gypsum core to better stick to the paper shell. Fiberglass adds strength. This mixture, called slurry, resembles a thick gray paste. It is poured in a continuous stream directly onto the paper tape moving along the conveyor. Special devices evenly distribute this mass across the entire width of the paper. The edges of the bottom sheet of paper are neatly folded upwards, forming the sides of the future sheet. And at this moment, it is covered from above with a second tape of paper, from the back roll, like a lid. The result is an endless, perfectly even sandwich. Paper, gypsum mass, paper. This sandwich immediately passes between 2 rollers, or under a forming plate, which compress it to a precisely specified thickness, for example, ½ inch. Just formed, still soft and wet, the drywall sheet continues its journey on a very long conveyor, called the setting line. Its length can reach several hundred meters. While the sheet slowly moves, a real miracle happens inside it. The gypsum powder reacts with water, the same rehydration reaction occurs. The gypsum turns back into a solid stone, releasing heat in the process. If you touch the sheet at this stage, it will be warm. In a few minutes, the loose mass becomes hard enough to hold its shape. At the end of this long line stands a flying knife. This is a huge blade that moves in sync with the belt and, at the right moment, makes a quick, precise cut, slicing the endless sandwich into sheets of standard length, for example, 8 or 12 feet. This happens so quickly that the conveyor does not stop for a second. The cut sheets are now solid, but still very wet. They contain excess water that did not participate in the chemical reaction. It needs to be removed. Therefore, a special device flips the sheets and feeds them into the most large-scale structure in the factory, a multi-story drying chamber. This is a giant labyrinth consisting of several levels, each of which is a conveyor. The drywall sheets slowly move along these levels back and forth, covering a path of several hundred meters inside this huge furnace. Hot air circulating inside gently evaporates the excess moisture from them. The temperature here is controlled very carefully. It is necessary to remove only the free water, without damaging the crystal structure of the gypsum itself. This process can last about an hour. At the exit of the dryer appears our familiar product, a perfectly dry, light and durable sheet of drywall. But this is not the end yet. The final stage is finishing. 2 finished sheets are stacked face sides together. Their edges are perfectly trimmed to be even and clean. A paper tape with information about the manufacturer and product type is glued to the end. After this, robotic manipulators with inhuman precision and grace lift the finished sheets and stack them in perfectly even stacks on pallets. Each stack is wrapped in protective film, marked and sent to the warehouse. From there, it will go to construction sites to become part of someone's home, having transformed from a simple gray stone mined from under the ground into a smooth and cozy wall. The production of drywall is like a barometer of the health of the construction industry. When the economy is on the rise, people are actively building new houses and renovating old ones, and the demand for drywall sharply increases. The factories that produce this product work at full capacity, and the stream of trucks delivering finished sheets throughout the country becomes endless. The heart of this production beats in unison with the rhythm of the real estate market. Geographically, this industry also has its centers. Although drywall factories are located throughout the country, to be closer to large construction markets, the mining of the main raw material, gypsum, is concentrated in certain states. The leaders here are states like Texas, Oklahoma, Kansas, Nevada, and Iowa. Every year, over 6 million tons of styrofoam are produced worldwide. But what if we told you that this lightweight material hides technologies that seem like science fiction? It all starts with oil, goes through boiling reactors, multi-ton extruders, and gas magic to become perfectly porous blocks. And what's most surprising, all of this is increasingly being created from trash. How exactly does plastic get a second life? And why might styrofoam be banned in some countries in just a few years? Watch until the end, because the finale will surprise you. The production of styrofoam is a complex multi-stage process that begins with a raw material, most often polystyrene. Polystyrene granules are the primary raw material for the production of styrofoam and other plastic products, and their production begins with a chemical process called the polymerization of styrene. First, the monomer styrene is obtained, a colorless liquid that is a product of oil refining or chemical synthesis from petroleum fractions. In special reactors, under controlled temperature, pressure, and the presence of catalysts, styrene monomers bind to each other, forming long polymer chains, polystyrene. This process occurs in several stages, where parameter control ensures the required degree of polymerization and final physical properties, such as strength, flexibility, and thermal conductivity. The substance transforms from a liquid state into a viscous plastic material. Next, the polystyrene is cooled and formed into large briquettes or granules. For granulation, the molten polystyrene is passed through special extruders, which extrude the plastic mass through numerous thin holes, similar to how dough comes out of a pastry bag. When the thin strands come out, they are quickly cooled in water baths or air streams, and, with the help of cutting equipment, are cut into small granules of a standard size. The most acceptable are grains from 0.04 to 0.2 of an inch. In recent years, a significant portion of the produced styrofoam contains secondary polystyrene. In the United States, this figure reaches 25% of the total volume, which helps to reduce the environmental impact of the industry. The introduction of modern technologies allows for a reduction in the emission of volatile organic compounds, including pentane, by about 30% compared to previous decades. The granules have a uniform shape and size, which facilitates further transportation, storage, and dosing in the styrofoam production cycle. They are supplied to factories in large bags or silos, from where they are sent to the drying stage as needed to remove moisture. The news is that modern manufacturers are increasingly implementing technologies for recycling used and spent plastic products back into polystyrene granules, thereby reducing the environmental impact and increasing economic efficiency. This cyclical process allows not only to obtain new granules, but also to reduce energy consumption and harmful emissions, which is important for the sustainable development of the industry. The production of styrofoam in the US and worldwide is steadily growing due to increasing demand in the construction, packaging, and automotive sectors. Annually, global production capacities for expanded polystyrene exceed several million tons. The demand for thermal insulation materials is growing at an average of 4 to 6% annually, which stimulates investment in new technologies and line modernization. polystyrene granules are delivered to the Styrofoam manufacturing plant, usually in specialized containers. The most common method is large industrial bags that hold from 1,000 to 3,000 pounds of granules at once. Such bags are loaded onto trucks or containers for transport. Sometimes the granules are transported in sealed containers, silos, or large plastic containers that protect them from moisture, dust, and foreign impurities. Delivery is handled with particular care in regions with high humidity, as even a small amount of moisture in the granules will negatively affect the quality of the styrofoam. At ports or logistics centers, the granules are unloaded using forklifts and transferred directly into the factory's silos. From there, they are fed through pneumatic transport systems, or conveyors, to the drying and preparation zones for further processing. The entire delivery chain is a carefully organized process that minimizes the contact of granules with the environment and contamination. The good news is that thanks to modern packaging and transportation methods, most factories receive already dry, clean granules, ready for the uninterrupted start of the styrofoam production line. This significantly improves the quality of the final product and reduces production losses. The energy required to produce 1 cubic foot of styrofoam is approximately 1 kilowatt-hour or less, which has been subject to optimization in recent years, taking into account environmental standards. When polystyrene granules enter special heating machines, one of the most important stages of styrofoam production begins: the partial melting of the raw material and the formation of a porous structure. These machines are usually extruders, large cylindrical devices several feet long, in which the granules are heated to 320 degrees Fahrenheit. Inside the cylinder, a screw rotates, a spiral blade that slowly pulls the granules forward, simultaneously mixing and heating them to the technological temperature. As the granules pass through the extruder, the heat combines with mechanical friction, causing the polystyrene to transition from a solid to a viscous, almost liquid state. This process is called plasticization, or melting. At this stage, the granules do not completely turn into liquid, but acquire a thick, cream-like consistency, which allows them to easily pass through the screw and forming holes. It is to this molten mass that a blowing agent is introduced, a special gaseous substance, most often pentane, a representative of environmentally safe volatile organic compounds. The blowing agent is added in a controlled amount so that it begins to evaporate in this hot environment, forming gas bubbles that become cavities inside the material. In the thick cream, thousands of tiny gas bubbles gradually appear, evenly distributed throughout the mass. These gas pores are the future structure of styrofoam, providing its lightness and thermal insulation properties. The process happens very quickly, and the temperature along with the pressure in the extruder are controlled by computer systems that maintain optimal conditions for pore formation. Next, this gas-saturated, but still viscous mass passes through a mold or extruder plates with holes of a certain size. There it is expanded into sheets or blocks of the required thickness. Immediately after exiting the mold, the material is cooled by a water or air cooling system, which fixes the pore structure, making the material hard, but at the same time very light and resilient. Simultaneously, the material is subjected to a cooling system to stabilize its structure. Rapid cooling fixes the formed pores so that the styrofoam does not collapse. As a result, a lightweight, porous material with a density of approximately 3.5 pounds per cubic foot is obtained, depending on the type of styrofoam and the customer's requirements. Next, the styrofoam is cut into sheets or blocks of specified sizes, often 4 feet by 8 feet, which is the standard in construction. These sheets undergo quality control, including checking for compressive strength, water absorption, and thermal insulation characteristics. The total weight of such sheets depends on the density used, but usually ranges from 5 to 25 pounds. The product is packaged and labeled for transport. It is expected that by 2030, market growth and technological progress will make styrofoam an even more environmentally friendly and versatile material. Every year, over 600 million tons of scrap metal are recycled worldwide. And it is from this that the heart of a railway wheel is born. Steel that can withstand a pressure of 145,000 pounds per square inch. Imagine, rusty cars and old beams in a fiery dance in an electric furnace are transformed into a molten lake of metal. But how does this chaos become a perfect wheel, capable of carrying thousands of tons across continents? In this video, we will reveal the secret of creating a railway wheel, from volcanic smelting to the secrets of heat treatment. Watch until the end, and you will learn a stunning fact that will change your perception of trains forever. It all begins in the recycling yard, because the heart of a railway wheel is steel, 100% made from recycled raw materials. Carefully selected scrap metal, old cars, beams, industrial equipment, is loaded into a giant ladle and heads to an electric arc furnace. This is a true industrial volcano. Amidst a deafening roar and dazzling flashes, 3 massive graphite electrodes are lowered to the scrap. An electric current of such strength is passed through them that it creates an arc with a temperature reaching 3,000 degrees Fahrenheit. In a matter of hours, tons of solid metal are transformed into a boiling, sparkling lake of molten steel. During this process, metallurgists take samples, analyzing the chemical composition in a laboratory. Based on these analyses, precisely measured portions of alloying elements are added to the melt. Manganese for wear resistance, silicon for strength, carbon, and vanadium. The goal is to obtain a unique chemical recipe for steel, optimized for the extreme operating conditions of a railway wheel. When the steel reaches the ideal composition, the furnace is tilted, and a stream of white hot metal weighing tens of tons is poured into a huge ladle. From here, the stage of shape creation begins. The ladle is moved over a row of cylindrical graphite molds. A bottom pouring method is used. The metal is fed into the molds from below through a system of channels. This is done to reduce the turbulence of the flow and prevent slag and other impurities from entering the casting, ensuring maximum purity of the future wheel. For about 20 minutes, the steel solidifies, and the hot, still red cylindrical blocks, called blanks, are extracted from the molds. This is just a rough hint of the future wheel. Now begins the stage where brute force transforms the blank into a refined engineering product. The blank is heated again in a furnace to a plastic state, approximately to 2,250 degrees Fahrenheit, and sent under a press. This is a hydraulic machine with a force of 4,000 tons. The forging process takes place in several stages. First, the press upsets the blank, making it shorter and wider. Then it is moved to the first die, which begins to form the main elements: the rim, the plate, and the hub. The next step, a powerful punch pierces a hole in the center for the future axle. After this, the red-hot blank, already resembling a wheel, is immediately transferred to a rolling mill. Here it is, clamped between several powerful rollers that with enormous pressure, roll and form the precise profile of the rim and flange. This process not only gives the wheel its final shape, but also works the metal's structure, refining the grain and making it significantly stronger and more resistant to crack formation. After rolling comes the most important stage, which endows the wheel with its unique dual properties: heat treatment. The wheel must be both hard and tough at the same time. Its running surface must be extremely hard to resist wear, while the plate and hub must be softer and more ductile to absorb shocks and not crack. For this, the entire wheel is uniformly heated to a temperature of about 1,550 degrees Fahrenheit. Then, at a key moment, a special spray ring delivers powerful jets of water exclusively to the rim and flange of the wheel. This instantaneous cooling, or quenching, drastically changes the crystal structure of the steel on the running surface, making it extremely hard. At the same time, the plate and hub cool slowly, in the air, which allows them to retain a more ductile and plastic structure. After this, the entire wheel undergoes a final tempering, heating to a lower temperature, about 1,000 degrees Fahrenheit, to relieve the internal stresses that arose during quenching and make it less brittle. Even after such complex processes, the wheel is not yet ready. It has the right strength, but its surfaces are rough, and its dimensions are imprecise. The machining stage begins. The wheel is mounted on massive computer-controlled lathes. Cutting tools remove thin layers of metal, turning the rolling profile and flange to ideal dimensions with an accuracy of thousandths of an inch. The central hole for the axle is separately bored. This operation requires the highest precision, as the wheel must be press-fitted onto the axle with enormous force, creating a connection stronger than a weld. The final stage is total quality control. Safety here is an absolute priority. Each wheel undergoes a series of non-destructive tests. It is inspected with ultrasound to detect any hidden internal defects, such as voids or cracks. The surface is checked using magnetic particle inspection to detect microscopic cracks invisible to the eye. Laser scanners and sensors check every dimension. And only after the wheel has passed all these checks does it receive its marking and is considered ready. Thus, the journey from rusty scrap to a shiny railway wheel is complete. It is a quiet triumph of engineering that allows millions of tons of cargo to safely cross the continent. Statistics on rail transport in the US illustrate the loads that each wheel withstands. American railroads move about 1.5 billion tons of freight annually. The average weight of a freight train is almost 4,000 tons, and its length can exceed a mile, with 100 to 150 cars. The weight of a standard loaded freight car can reach 286,000 pounds, and in some cases, 315.5 thousand pounds. This weight is transmitted through 8 wheels, creating a static load of over 35,000 pounds on each wheel. At the point of contact between the wheel and the rail, the pressure reaches high values. The contact area is comparable to the size of a dime. In this area, the pressure averages 90,000 pounds per square inch, and peak values can exceed 145,000 psi. Such loads exceed the yield strength of the steel, causing elastic deformation of the metal at the point of contact with each rotation. The standard diameter of a wheel for 100-ton capacity freight cars is 36 inches. For 70-ton cars, 33 inches. The weight of a 36-inch wheel is about 800 pounds. During its service life, an average freight wheel travels from 500,000 to 700,000 miles. There are over 1.5 million wheels in service on the US rail network. Each of them undergoes ultrasonic and magnetic particle inspection to detect internal or surface defects. Standards developed by the Association of American Railroads regulate all parameters, from chemical composition to rolling profile tolerances, to ensure safety and reliability in operation. You have to agree, there is something romantic about trains. And now you know exactly what kind of wheels are making that clatter. Every hour, over 4.5 million tires are discarded worldwide. But in Nigeria, a country with over 220 million people, old tires are not just trash. They are a currency for survival, an underground business, and even art. Here, worn-out rubber doesn't go to a landfill. It's taken apart, rolled on bicycles, cut by steel jaws, and baked into colorful tiles. How did poverty, ingenuity, and chemistry create a whole shadow industry? And what unexpected secret is hidden in one of the largest pyrolysis furnaces in Lagos? Watch until the end, and you'll see what they probably don't show in textbooks. Nigeria is the most populous country in Africa, home to over 220 million people. For many of them, a car is the primary means of transportation and doing business. Millions of passenger cars, minivans, trucks, and motorcycles travel the country's roads daily, inevitably wearing out their tires. The more vehicles, the larger the flow of used tires. The condition of roads in many regions of Nigeria is, to put it mildly, far from ideal. Numerous potholes, ruts, gravel surfaces instead of asphalt, and the general neglect of the road network lead to extremely rapid and aggressive tire wear. A tire that could last 40 or 50,000 miles in countries with high-quality roads might become unusable 2 or even 3 times faster in Nigerian conditions. A significant portion of cars in Nigeria are imported used vehicles, known as tokunbo. They often arrive from Europe, the United States, and Asia, with already significantly worn tires that require almost immediate replacement after purchase. This creates an immediate stream of old tires into the waste market. Due to economic hardships, many Nigerian drivers cannot afford expensive and high-quality tires from leading brands. They are forced to choose the cheapest options, either low-quality new tires, mainly from Asian countries, or already used tires. Both options have a very short service life, which creates a continuous cycle of buy, drive a little, throw away. Until recently, the country effectively had no established and efficient state system for collecting and recycling tires. Without proper disposal infrastructure, old tires simply accumulated in makeshift dumps, on roadsides, in vacant lots, and in water bodies, turning into a serious environmental threat. Only recently have entrepreneurs begun to see a business opportunity in this. The process of collecting tires in Nigeria is a fascinating, mostly informal, and multi-level system that operates not by government decree, but by the laws of the market and simple economic benefit. At the heart of the entire chain are thousands of individual collectors. These are often young men or people with low income, for whom collecting waste is their main livelihood. So, where do they collect them? The main source is tire shops and car repair workshops. Drivers leave old tires after a replacement. For the workshop owner, this is trash that needs to be disposed of. A collector pays him a small amount, or simply takes them for free. Collectors also literally patrol their neighborhoods, looking for abandoned tires in makeshift dumps and on roadsides. The tires are rolled by hand, transported on wheelbarrows, bicycles, or small 3-wheeled scooters. One old tire can cost from 50 to 200 naira. That's a few American cents, depending on its condition and size. It's not much, but by collecting several dozen a day, one can make a living. Collectors rarely deal directly with large factories. They sell their harvest to local middlemen. Middlemen are small entrepreneurs who own a small truck or pickup and a place for storage, usually just a fenced-off plot of land. They buy tires from dozens of street collectors. This is where the initial accumulation happens. They might collect several hundred or 1,000 tires before the batch becomes large enough for further sale. This is where those mountains of tires appear, but on a local scale. In the yard of such a middleman, you can see piles of tires that he accumulates, waiting for a good price or a sufficient volume for transport. Basic sorting might happen here. For example, separating truck tires from passenger car tires. The middlemen make their profit on volume. They buy cheap from collectors and sell for a higher price to large processors. Large recycling companies are at the top of the chain. Companies engaged in pyrolysis or the production of rubber crumb are the final buyers. These are recycling plants like Freetown Waste Management Recycle or large pyrolysis facilities. They make deals with the middleman. The aggregator loads a large truck of 5 or 10 tons and brings the tires directly to the plant. The plant accepts the raw material, weighs it, and pays the middleman by tonnage. This is where the final, professional sorting takes place. The tires are inspected, cleaned of dirt and foreign objects before being sent to a shredder or pyrolysis furnace. As soon as the tires arrive at the recycling site, they head down one of 2 main paths. The choice of path depends on the technologies the company possesses and the final product it wants to obtain. Pyrolysis is a method used by large industrial plants. The goal is to break down the tire into its basic chemical components to obtain industrial raw materials. Tires cannot be loaded into the reactor whole. First, they undergo tough preparation. Powerful hydraulic shears cut out the bead ring from the tire, a thick steel wire that ensures a tight fit on the rim. Then the tire is sent to an industrial shredder. The machine's steel jaws tear and cut the rubber into pieces a few inches in size, turning it into a uniform mass resembling coarse chips. The prepared rubber pieces are loaded into a sealed metal reactor. This is the heart of the entire process. The reactor is heated to high temperatures, 800 degrees Fahrenheit, but the key condition is a complete absence of oxygen. Because of this, the rubber doesn't burn. Instead, its long polymer molecules begin to break down into simpler substances. As a result of the heating, a mixture of 3 fractions is formed: a gaseous fraction, a liquid fraction, and a solid residue. After the cycle is complete, the factory obtains 3 products ready for sale. The first is pyrolysis oil, which is used as fuel for industrial furnaces and boilers. Carbon black is sold to manufacturers of paints, plastics, and new rubber products, and the steel wire is collected by magnets, pressed into briquettes, and sold as scrap metal. Another path for recycling old tires is mechanical recycling and upcycling. This path is chosen by companies like Free Recycle, which create finished consumer goods. There is no chemical reaction here, only physical transformation. The tires also go through shredders, but the goal here is to obtain clean rubber crumb of various sizes. During shredding, powerful magnets extract steel fibers from the rubber mass, and air separation systems blow out textile fibers. The output is clean rubber granules. The rubber crumb is poured into a large mixer. 2 key ingredients are added to it: polyurethane glue and pigments. The glue will bind the rubber particles together, and the pigments will give color to the future product. The resulting mixture is thoroughly mixed until uniform. The colored rubber mass is placed in metal molds of the desired configuration, for example, in the shape of paving tiles or mats. Next, the mold is sent under a hot press. High temperature and pressure activate the glue, baking the crumb into a single, durable, and elastic product. This can be bright and safe paving tiles for playgrounds, durable flooring for gyms or garages, soles for shoes, or even entire flip-flops. A separate direction is upcycling, where whole tires or their large pieces are turned into original furniture, such as tables or chairs and other decorative items. Thus, depending on the chosen path, an old, unwanted tire is transformed either into a valuable industrial raw material or a new useful household item. Every year, over 40 billion coins are minted worldwide. But you'll never guess where it all begins. Imagine giant rolls of metal weighing 8,000 pounds, entering a workshop like armored trains. There, something incredible awaits them. Presses that strike with a force of 200 tons, and furnaces that heat up to over 1,200 degrees Fahrenheit. Every strike is a new story in your pocket. But there's one thing they don't show in any documentary film. And if you watch this video until the end, you'll be the first to find out. The whole show begins not with a shine, but with the dull scrape of metal, as huge coils, resembling giant toilet paper rolls, are brought into the workshop. Only this isn't cellulose, it's copper, zinc, nickel, or special alloys. These rolls are called coinage coils, and they look serious. Each coil weighs up to 8,000 pounds and is up to 13 inches wide, depending on the type of coin. The metal strip is slowly unwound, like a giant snake, and fed into a straightener, a system of rollers that removes waves, bends, and misalignments. Because precision is sacred, even a tiny bend of 1/100th of an inch can ruin the subsequent stamping. The strip thickness is up to 0.125 inches, and this thickness is controlled in real time by sensors, lasers, and automation. Everything is precise because otherwise the blanking press would simply fail or start making crooked blanks. Each metal is for its own denomination. Zinc strips with copper plating, for pennies. Copper-nickel alloys, for nickels, dimes, and quarters. Bronze alloys with manganese, for $1 coins, like the Sacagawea or US presidential coins. These rolls are not only heavy, they are also expensive. Every centimeter must be used wisely. Therefore, the metal also undergoes an automatic inspection for dents, cracks, and residual oxides. Defects are rejected immediately, cut off, and the strip moves on, like a well-sharpened knife. Next, it faces a press battle. But already here, in the preparatory stage, the fate of each future coin is shaped. Because if the strip isn't made perfectly, there will be no George Washington, no Abraham Lincoln. There will be scrap metal. After the metal strip is straightened, leveled, and approved, it slowly but surely enters the zone where its main trial awaits, the blanking press. And if you think this is some boring little press, then throw that thought out right now. This machine is a metal beast, a hydraulic monster that pounds the metal so fast that the human eye can't blink between strikes. These presses don't just cut out circles, they slam into the strip at a speed of up to 750 strokes per minute. Bam, 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 bam. It's like a mixer on steroids collided with a military ram. Inside, dozens of high-precision dies, similar to cookie cutters, only this isn't cookie dough, it's copper, zinc, nickel, bronze. And when they come down, perfectly round metal blanks fly out of the strip, which has been heated to a shine. Their diameter is clearly defined. These are the embryos of future money. They are still without portraits, without inscriptions, without shine, dull, matte, sometimes with burrs on the edges, but already with the right size, weight, and character. And now imagine the scale. One press can cut up to 14 blanks every second, or 800 to 1,000 pieces per minute. In a day, millions of circles. And this is just on one line. And there are dozens of such lines in the mint. When the die strikes, a dozen or two circles are cut from the strip with each blow, and the leftover metal, meaning everything between the circles, is instantly rewound, wound onto another coil, and sent for recycling. Nothing is wasted. Here, you know, money is even in the scraps. The blanks fly out onto a conveyor belt, hot, slightly discolored, with a light trace of oil and dust. They are collected in metal boxes, sometimes even poured like grain, straight from a chute. Clink, clink, clink. And this sound is simply hypnotizing. A metal rain of future coins. The air is thick with dust and lubricating vapors, smells of metal and money. Literally. Did you smell it too? So you've seen how circles are cut from dull metal, but that's not all. They are still raw, matte, a bit dirty, with oily marks from the press. They need a real spa day. So the first stage is washing. The circles are loaded into huge vertical drums that resemble washing machines, only the size of a bathtub. Inside, hot water around 140 degrees Fahrenheit with an acid solution and special detergents. The drum spins. The circles bang against each other like a foamy dance of metal balls. Everything is removed. Dust, oil, traces of oxides. The water hisses, steams. After this, drying. The drum tumbles the circles, drying them with hot air so that not a single drop remains on the surface. Wet blanks are death for stamping. Next, a real fire ritual, the annealing furnace. These metal circles race through a long furnace, 12 to 40 feet long, where the temperature reaches a crazy 1,250 degrees Fahrenheit. The metal becomes red hot, but doesn't melt. It softens. It's like warming up the body before hard work, so you don't tear a muscle. After the furnace comes rapid cooling. The circles fall into a bath of cold water, about 50 degrees Fahrenheit. This temperature shock makes the metal stronger and more elastic. Then the circles are coated with a thin layer of graphite lubricant, so that during stamping, the press doesn't stick or scratch the surface. This is the final cycle of drying and preparation. Now they are shiny, flexible, and ready to take on a pressure of 400,000 pounds per square inch during stamping. From washing and baking, the circles are no longer just pieces of metal. They are real contenders for the role of a coin. But all they have now are clean, smooth discs, without faces, letters, or shine. And now it's time to give them character, a soul, and a history. The tool for this is the coining press. A huge steel machine stands like a rock in the hall, with a mechanism capable of pressing with a force of up to 200 tons. It presses so hard that sparks don't fly from it, but the metal on the circle sinters and takes shape with incredible precision. When a circle enters the press, it is clamped between two dies, an upper and a lower one. Each die, like a carved hammer, imprints all the details into the metal. Portraits of presidents, coats of arms, dates, inscriptions, fine lines, and even the smallest letters. All this is incredible microwork, executed with surgical precision. In an instant, the press strikes the circle with insane power, and the metal from fine grains turns into a pattern that thousands of people will see in their pockets and wallets. And it's not just one strike. Some machines have double-sided stamping, where both the obverse and reverse are applied at once, all in a fraction of a second. The speed is impressive. One machine shoots out 750 coins per minute, and dozens of such presses work simultaneously in the workshops, so tens of millions of coins are produced in a day. It's like music, only instead of drums, it strikes on metal, and instead of a melody, a chain of shine and power. After stamping, the coins don't shine right away. They are still warm, and may have small burrs. Next on the conveyor, the coins move to inspection machines. Laser sensors determine the exact diameter and thickness. Visual cameras search for defects in the relief and surface. The human hand is still necessary for rejecting flawed specimens. And so, the coin has passed through all the infernal stages, from the hot furnace to the press strike, and is now ready for its grand debut into the real world. But before that, a final march through the packaging area. Coins come off the conveyor, clinking, flashing, rustling. They are no longer counted individually. They are counted by weight. They are poured into special metal bags or large containers, similar to coffee bags, only each one holds up to 4,000 coins. For example, a standard bag of quarters is $1,000, and the weight of such a package is about 60 pounds. Impressive, right? When a bag is filled, it is hermetically sealed. A seal and a barcode are applied. Next, onto a pallet with hundreds of its brethren. All this into huge trucks that deliver money across the country. To banks, ATMs, stores, soda machines, the military, wherever. And sometimes they are packaged in rolls, small paper tubes. These are for retail circulation. They pour into boxes, clicking like casino chips, and you can already hear them clinking in someone's cash register. This is how an everyday miracle is born. You drop a coin into a parking meter, and behind it is a whole story from a hot workshop, fire, hydraulics, and people who give metal life. Every day, over 2 billion square feet of glass are produced worldwide, enough to cover the entire area of New York City. But have you ever wondered where the glass you look through every day comes from? Its journey begins deep in a quarry, where pale white sand from Illinois has been waiting for millions of years. And it ends on the surface of molten tin in the form of a transparent, seamless sheet. This video will reveal all the secrets of float glass, from volcanic furnaces to laser marking. And at the end, you'll learn one thing that even the largest manufacturers keep hidden. Don't switch. It's about to get truly transparent. Before hot sand becomes a clear window, it all starts in a quarry. The main raw material for float glass is high-quality quartz sand. It must be almost perfectly pure, with a silicon dioxide content of over 99.5%. Such sand is extracted from special deposits, usually deep underground, where it has rested for millions of years in geological tranquility. One of the most valuable is Ottawa sand from Illinois, pale white, as fine as flour, and extremely pure. Quarries operate like giant anthills. Excavators clear away layers of earth, and 40-ton class dump trucks deliver the sand to crushing plants. Then comes dry screening. The sand is cleaned of stones, organic matter, and the smallest impurities. Here, up to 15% of the total volume is rejected. Because if even one crystal of impurity gets into the melt, it can distort the light in the finished glass. Besides sand, glass includes several other components. Soda ash lowers the melting temperature. It's brought from salt deposits, particularly from Wyoming, in 50-pound bags or in bulk in railroad hopper cars. Limestone stabilizes the structure. It's supplied from quarries and crushed to a dust with a diameter of less than 0.04 of an inch. Dolomite, aluminum oxide, saltpeter, and also glass waste, so-called cullet, crushed broken glass from previous batches. It helps reduce energy consumption from melting by up to 25%. After primary cleaning, all components are mixed in precise proportions, which are kept as a trade secret. A giant mixer the size of a 2-story house prepares the glass flour mixture. The finished mixture is transported to the production facility by trucks, sometimes by rail or even barges, depending on the factory's location. The storage temperature must be controlled. No moisture, no extra organic matter. The warehouse resembles a sterile grain elevator with silos of 20,000 cubic feet each. Next, the batch is automatically fed into the glass melting furnace, where in just a few minutes, everything that was just sand and dust yesterday will turn into a boiling ocean of glass. The mixture, having just completed a complex journey from the quarry to the mixer, finds itself at the heart of production, the glass melting furnace. This is a true industrial volcano, over 200 feet long, with a temperature of up to 2,900 degrees Fahrenheit in the melting center. There's no open flame here. Only walls of refractory brick heated to white hot and gas burners that maintain the temperature with degree precision. The raw material is fed automatically, precisely dosed, several tons per hour. In the first 30 or 40 feet of the furnace, melting occurs. The components melt and merge into a red-hot, viscous mass, similar to honey, but 500 times hotter. Next, the homogenization zone. The mass is mixed and matures until all bubbles, lumps, and impurities disappear. And only after this does it calmly flow onto metal. This is where the magic of float begins. In the second stage, the mass enters a bath of molten tin, heated to 1,100 degrees Fahrenheit. The glass literally floats on the metal, spreading out into a uniform ribbon. It's thanks to surface tension and the perfect flatness of the tin that a mirror-smooth surface is formed on both sides, without polishing, without presses. The thickness is controlled by stretching. Special rollers or electromagnetic fields stretch, or conversely, compress the glass ribbon. This way, you can get glass with a thickness from 1/16 to 3/4 of an inch, depending on the client's needs. The length of the tin bath is over 150 feet, and the glass slowly floats along it at a speed of up to 25 feet per minute, cooling along the way to 1,000 degrees Fahrenheit. This is a very critical moment. Any skew, sharp movement, or temperature change, and the glass surface will be ruined. But even at this stage, it's not ready yet. Next, the annealing zone. The glass ribbon passes through a long tunnel where it cools by a few degrees per minute to relieve all internal stresses. If this isn't done, the glass could later crack on its own, without any load. Its surface is like an ice sheet without a single scratch. If you look at an angle, you can see your own reflection, as in a mirror. The size of the sheet is impressive, up to 10 feet wide and over 30 feet long, completely transparent. In this state, the glass enters the cutting zone. Before it's cut, a computer scanning system analyzes the entire surface, looking for microcracks, inclusions, dust, stress. Any finding, and the sheet is rejected. The rule here is, better to reject early than to have glass explode in a truck or a shop window. Cutting is not mechanical, like in the old days. Now, it's laser or roller scoring. A microblade, similar to a diamond one, makes a line, and then gentle pressure breaks the glass precisely along the trajectory. Sometimes sheets are cut immediately to order, for example, 24 by 36 inches for construction glass, or the size of a screen for a Tesla. Others go in standard formats to warehouses, where they will be stored vertically, on racks with rubber pads, so that not even a shadow of a scratch spoils the perfect shine. After cutting, the calibration stage. The sheets are checked for thickness, geometry, and straight edges. High-definition cameras scan every centimeter. Lasers analyze the angles. There are almost no human hands here, only at the final stage, when workers in gloves mark the perfect sheets. In a world where glass has perfect transparency and no visible seams, marking is its name, passport, and the master signature all in one. It is in the marking zone that each piece of glass is given its identity: where, when, by whom, and for what it was created. The marking may look modest, a small logo in the corner, but it carries dozens of parameters: manufacturer's name, type of glass, date of production, shift, line, factory, and sometimes even the batch composition. The most common marking method is laser etching. A special laser vaporizes microscopic dots on the glass surface, creating a wear-resistant, matte inscription. It's unnoticeable from a distance, but easily readable up close. The font thickness is less than 1/10 of an inch. This inscription cannot be removed without damaging the glass, which is why it's often used as an anti-vandal code in safety or tempered glass. Sandblasting engraving is used for decorative or premium glass. An abrasive is applied to the glass under pressure through a stencil, creating a raised matte mark. This is how, for example, antique mirror glass or large facade elements are marked. And there's also ceramic ink marking. This method is used before the tempering stage. A special paint with minerals is applied by a printing method, often through a stencil or with a digital printer, and then baked at a temperature of over 1,100 degrees Fahrenheit. Such marking is colored, noticeable, and very durable. It doesn't wash off, doesn't rub off, doesn't fade. Marking can be both technical and brand related. For example, on the windows of elite houses, the manufacturer's logo is often left with pride, as in, yes, this is St. Gobain, or Pilkington. In some projects, marking is even used for authenticity control. For example, glass for armored vehicles or government institutions receives a serial number and a QR code. The final stage is documentation. Each sheet gets a record in the system, like in a hospital: what kind of patient it is, when it was born, what its properties are, and where it's going. This is important because glass doesn't always go out immediately. Some batches are stored for months until their time comes. Every year, over 300 million electric motors are manufactured worldwide, from miniature ones that spin coolers in laptops to giants that power trains, factory lines, and mine elevators. And each one of them is not just a coil of wires and iron, but a complex system of dozens of precisely calibrated parts. How is the heart of a machine born? Why is winding similar to weaving, and balancing to jewelry making? And how does one spark power a rotation that will last for thousands of hours? Let's take a look behind the scenes of one of the greatest technical processes: the creation of an electric motor. Inside every electric motor is a true mechanical electrical universe. The main components of a motor are the stator, rotor, shaft, bearings, housing, as well as a cooling system and terminal box. The stator is the stationary part, located in a circle inside the housing. It's what creates the magnetic field that makes the rotor spin. Inside the stator is a core made of layers of thin electrical steel, which reduces losses from eddy currents. In the slots of the core is a winding of copper wire, connected in a special way to create a rotating magnetic field. The rotor is the moving part inside the stator. It either has its own winding or is made in the form of a squirrel cage. Aluminum bars cast into a steel core, which form closed current loops. When the stator's magnetic field interacts with the rotor, it starts to rotate. The shaft is a rod that passes through the rotor and extends outside the housing. It's on this shaft that pulleys, impellers, reducers, or other drives are mounted. It transmits rotation to the mechanisms. The shaft must be precisely centered. Otherwise, the motor will vibrate and wear out quickly. Bearings, usually two, one at each end of the shaft. They ensure smooth rotation with minimal friction. For reliability, they are lubricated with special greases or are sealed. The housing protects the internal elements from dust, moisture, and mechanical damage. It often has fins for heat dissipation or even a fan. The material is cast aluminum or cast iron, depending on the power and purpose of the motor. The cooling system, most often it's simple air cooling, A fan on the shaft drives air flows through the housing. In large industrial motors, liquid cooling or external air circulation through special channels is used. The terminal box is on the outside of the housing. This is where the power cables are connected to the stator winding. Inside, contacts, clamping screws, and sometimes temperature sensors. In the depths of the factory, in a workshop that smells of varnish, metallic dust, and warm insulation, stands a giant stator. A stationary ring with slots around its circumference. This is its core, made of thin steel sheets, tightly pressed together. In each slot of this ring will lie copper wire, carefully laid, loop by loop, turn by turn, because whether the motor will rotate at all depends on this. Before starting the winding, the stator frame is thoroughly prepared. The slots are lined with special insulating liners, like nests for the wire. These are materials that withstand high temperatures, vibrations, and electrical loads. And only when they are sure that the insulation is perfect, the winding machine is started. The machine, resembling a giant spool that unwinds copper wire from a bobbin, wraps it around guides and lays it in the slots. Everything is automated, but under the supervision of a specialist. One sharp movement, and the wire could lay with a kink or snag the insulation. And that's a potential short circuit. For powerful or non-standard motors, winding is done by hand. A worker inserts the wire in a loop, pulls it through with a tool, presses it to the bottom of the slot, secures it, and tightens it. The work is similar to weaving, but with shiny copper and immense responsibility. Each coil, and there are dozens of them, must be identical, symmetrical, and correctly oriented. After the first layer of winding is completed, interphase insulation is laid, and then the second layer is placed. The wire forms closed loops, phases, which are then connected in a star or delta configuration, depending on the motor's setup. Then, the wires are secured with strings or plastic fasteners, the tension and geometry are checked, and if necessary, adjusted by hand. And finally, impregnation with varnish or epoxy resin, so that all this doesn't shift even a micron under vibration and temperature under load. If the stator is the skeleton, then the rotor is the muscle. It moves, rotates, creates torque. It's not visible when the motor is running, but it's what drives everything, from a fan to a train. At the core of the rotor is a steel shaft, long and powerful. Around it, the core is mounted, a set of thin electrical steel sheets stacked into a cylinder. The sheets have slots. These are for the conductors. This is where the most interesting part begins, creating the winding that will make the rotor come alive. One of the most common options is the squirrel cage. Aluminum or copper bars are inserted into the slots, and both ends are cast into rings, like a hoop around a cage. This creates a closed current loop. Such a design doesn't need to be connected directly. Current is induced inside automatically as soon as the motor starts. It's a simple, reliable, and mass-produced option for industry. But if the motor is more complex, more powerful, then classic windings are used. A worker manually lays copper wire in each slot, carefully tightening it, bending it at an angle. Here, symmetry, precise geometry of the turns, and perfect insulation are important. The wire must lie right, not touching the metal anywhere, not crossing over, not being too tight or too loose. A mistake, and the motor will overheat or fail. The rotor windings are then connected in a specific sequence: star, delta, or another type of connection. Everything is secured, insulated, and sometimes varnished. The insulated ends are led out to slip rings or brush assemblies, depending on the design. After this, the rotor is balanced, as it has to rotate at speeds of thousands of revolutions per minute. Any extra 100 grams on the edge, and everything will vibrate, hum, and heat up. The result? A compact, shiny cylinder with windings of copper wire or closed bars. It will be inserted into the stator, and the magic of converting electricity into motion will become possible. It all starts with checking dimensions and tolerances. The gap between the rotor and the stator, the so-called air gap, must be very small. If it's too narrow, friction will occur. If it's too wide, the magnetic field will be weak, and the motor will lose efficiency. The rotor is mounted inside the stator via bearing assemblies. Sometimes special guides or hydraulic presses are used for this. The rotor shaft must rotate perfectly straight, otherwise everything will vibrate or break down within a week. At the ends of the rotor shaft, sleeve or rolling bearings are installed. They allow the rotor to rotate without friction. The bearings are placed in so-called end shields, which are then attached to the motor housing. All surfaces are pre-lubricated with special greases to ensure durability. The ends of the stator and, if necessary, rotor windings are led out to the terminal box. Here they will be connected in the required circuit, star, delta, or another. In complex motors, temperature sensors are installed to detect overheating before a failure occurs. The motor is now assembled, stator and rotor in the housing, wires connected, bearings in place. But it's too early to start it. First, varnishing, drying, balancing, and testing, all like a ritual before the birth of a real machine's heart. In a spacious room with a specific smell of epoxy resin, the stator windings, and sometimes the rotor, are coated with electrical insulating varnish. This isn't just for dust protection. The varnish strengthens the structure, secures the wires so they don't vibrate at high speeds, and prevents moisture penetration. Application is either by dipping in a bath or by spraying. The motor is completely submerged in a tank of varnish, then removed and left to drain off the excess. Next is drying in a thermal chamber at a temperature of 250 to 300 degrees Fahrenheit. This stage resembles baking. The varnish polymerizes and forms a hard protective film. After varnishing, the most sensitive stage, the motor is installed on a balancing stand. The system is like a huge record player. The motor rotates at high speed, and sensors detect the slightest deviations. Even a few grams of excess mass on the rotor can cause vibration that will destroy the bearings, shorten the service life significantly, or even ruin the motor. To eliminate the imbalance, engineers drill microscopic holes in the heavier part of the rotor, removing excess metal. This is almost a jeweler's craft. The finished motor is sent to the test stand. Here it comes to life for the first time. It's connected to a power supply. Rotations, noise, heat, current consumption are recorded, and efficiency and power are measured. Everything is documented. The motor's passport contains dozens of parameters. If the motor passes all tests, it's packaged, a seal is applied, and an instruction manual is added. And very soon, this motor could be working on a conveyor, in an elevator, or in an electric train, wearing down metal and converting current into motion, without rest for tens of thousands of hours.